So another application of derivatives comes in what's called the mean value theorem. So let's just write out the theorem first, and then we'll look at how we can use it and what it means. So let's let f be continuous over the closed interval a, b. Okay, so a and b are included here. And differentiable over a, b, not included. So it doesn't need to be differentiable at a or b, but it does need to be continuous at a and b. Then there exists at least one point C in A and B. Okay, so this symbol right here means in this interval, such that f prime of C equals f of B minus f of A divided by B minus A. Okay. So the right-hand part of this equation you might recognize as the slope, right? Specifically, it would be the slope of the secant line connecting A and B. So this says that there must be some point on this function where the derivative at that point is equal to the slope of the secant line between those 2 points. So let's just, draw a function and look at it doesn't matter what function or where it is, as long as it's continuous and differentiable. Okay. So just something like this. Let's say this is A, this is B. So we're only looking at this part right here, right? So we want to look at a secant line between these 2 points. Okay. And we're saying that whatever the slope of this secant line is, there must be some point in between these parts which has the same slope as that secant line. So it looks like it's probably somewhere around like right here on this one, right? If it has the same slope, then the tangent, that means that the tangent line at that point would have that slope. And two lines that have the same slope are parallel. So you'd be basically looking for a parallel tangent line. So it looks like it could be somewhere like right here, right? It'd be easier if we actually had numbers. We could actually find what it was. But just to kind of look at an idea of what this means first. So let's remember that if we think of this in terms of rate of change, right? So this the slope of the secant line is telling us the average rate of change between the points A and B. So what the mean value theorem is saying is that the instantaneous rate of change must at some point be equal to the average rate of change, right? So if you think about it, it's kind of another application of the intermediate value theorem for averages. Okay. So let's just look at an example of where we could apply this. So let's look at the f of x equals the square root of x over 0.9. Okay. So in order to apply the mean value theorem, we first need to show that it is continuous over that interval and differentiable over that interval. Okay. So, I think we've already shown a lot of these would be like, okay, we know that this function is continuous. The only time you really need to show the continuity is if there's a point in question, right? So like if you have the rational function like 1 over x, you have to make sure that 0 is outside of the interval that you're considering because it's not continuous on that interval. So here, the square root function is clearly continuous on this interval. It's at least right continuous at 0. We don't need to get held up on the nuances there about whether it's actually continuous or not. When you're only looking at a closed interval at that point anyway, you only are really getting right or left continuity. So it's not a big deal here. It is going to be differentiable over this interval. It's not differentiable at 0. We have shown that before, right? Because the derivative, which we can just find now because we're going to need it anyway, is 1 over 2 root x, right? So this point is not differentiable at 0, but this is fine over 0, 9, open, right? Not included. So this tells us that there's a point C such that f prime of C is equal to this secant line. So let's go ahead and find that point. Okay. So f prime of C is equal to f of 9 minus f of 0 divided by 9 minus 0. Okay. So this is going to be the square root of 9, which is 3, minus 0 over 9 minus 0 equals 1/3. Okay. F prime of C is 1 over 2 root C. This equals 1/3. So now it just becomes an algebra problem, right? So we're going to get the square root of C equals 3/2. So C is equal to 9/4. Okay. So at this point, if there is more than one point, you would get that point. But this tells us that there's only one point, which is at 9/4. So let's go ahead and investigate this graph here. Okay, we'll look at the square root of x. So we're looking between 0, 0, and 9, 3, just about right here. Okay. So we'll go ahead and throw the secant line up there, which is going to be a line with a slope of 1/3 and a y-intercept of 0 because it's going through 0, 0. So this is the secant line. Okay, so it's telling us that the derivative, the slope of the secant line 1/3 is equal to the derivative at the point 9/4, which is about 2 1/4. So 2.1 or 2.25 rather, about right here is where the slope is the same as that secant line. Okay, so if we graph the tangent line at the point, it would be equal, it would be parallel to that point. Okay, so if we just go ahead and graph f prime of x, then we can see at 9/4, 2.25, that should be where the derivative is equal to about 1/3, which we can see verify here. Okay. So it's very important we check these conditions. This isn't going to be true if we don't have those conditions. For example, if you have like the absolute value function in there and you're looking at the point A and the point B here, or if you just look at points directly across from each other. Okay, so like if we look at f of x equals the absolute value of x over -2, 2, for example, then f prime of c is never going to be equal to f of 2 minus f of -2 over 2 minus -2, which is going to be 0. Okay, F of 2 and f of negative 2 are both 2, so this is 2 minus 2, which is 0. F prime of c is never going to be 0, because f prime of z is either negative 1 or 1, and at 0 it doesn't exist, right? So the reason the mean value theorem fails here, so the mean value theorem fails because f is not differentiable at 0 and 0 is in negative 2 to 2, right? So we have to have those conditions in order for the mean value theorem to be true. So there's some interesting corollaries we could look at. There's a lot of corollaries of the mean value theorem. A corollary is like a consequence of the theorem that's not much harder to prove than the theorem. Like basically you don't need anything else to prove it. So a couple corollaries we can look at here. And we didn't actually go through the proof of the mean value theorem. The most common proof uses what's called Rolle's theorem, which is a more specific version of the mean value theorem. And we'll look at that in a second as well. So one interesting corollary is that if we let f be continuous over AB and differentiable over AB open, then if f prime of x is greater than 0 for all x in A to B, then f is an increasing function over A, B. Okay. So this maybe is not too surprising if you've been kind of thinking about what the derivative means up to this point. We're going to look at increasing and decreasing in the relationship with the derivative in a few videos. But the derivative being positive means that the function is increasing, right? That means that the slope is positive, and if the slope is positive, that means that the function is increasing. So the way that we can prove this, and you can flip this around, you can flip it around to f prime of x is less than 0, and then f is a decreasing function as well, and the proof is very similar. So definitely go ahead and try to prove that one on your own if you'd like. So the way that we prove this is actually by what we call a proof by contradiction. So we suppose that it's not true, and then we show that it leads to an incorrect conclusion. So suppose f is not an increasing function. So we need to write out what it means to be increasing, first of all. Then there exists, let's say, C and D, or let's write it like C, D in AB, such that C is less than D, but f of C is greater than f of D. Okay, so your input goes up, but your output goes down, right? That would mean that it's decreasing, so it's not increasing. Okay. So because everything is differentiable and continuous by the mean value theorem, there exists let's say H. We're using a lot of letters here, so let's go to H. Such that f prime of H equals f of D minus f of C over D minus C. So I guess now that I'm writing this, I could have just used A and B as the bounds on there. I decided to use C and D because it doesn't necessarily have to be your endpoints, but hopefully it's clear that if f is continuous over AB and differentiable over AB, and CD are inside that interval, it's also differentiable and continuous over CD. So the mean value theorem will still apply here. Okay, you're basically just shrinking that interval. So if it's continuous differentiable over the larger interval, it definitely is over the smaller interval within that interval. Okay, so the mean value theorem will still guarantee this. Okay, now, because f of C is greater than f of D and C is less than D, this is going to be a negative number. Okay. Meaning that, so what this is saying, to cut out the middle part here, this is saying that f prime of H for some H is less than 0. Okay. But this contradicts our assumption that f prime of x is greater than 0 for all x in that interval, which would include the smaller interval as well. So this is a contradiction. So f must be increasing. Okay. So if we assume it's not increasing, it leads to a contradiction. So therefore, it must be increasing. So this is another common proof technique where you assume the opposite is true and then show that it leads to a contradiction. So this will be useful as we explore the relationship between increasing and decreasing in the derivative. Okay, so real quick, just Rolle's theorem I did want to mention as well. So usually the way this goes is that Rolle's theorem is proved first, and then that is used to prove the mean value theorem. So let's look at that. And the way you prove Rolle's theorem is just to break it up into cases. So we let f be a continuous function. Okay, over the closed interval AB. And differentiable over AB, the open interval, such that f of A equals f of B. So this is a little bit different than what we had before. Then there exists at least one C in AB such that f prime of C equals 0. Okay. So this is an easy corollary of the mean value theorem. I just hesitate to call it a corollary because, again, most people prove Rolle's theorem first and then use Rolle's theorem to prove the mean value theorem. So then to use the mean value theorem to prove Rolle's theorem would be circular reasoning. So we didn't actually do that. We didn't prove the mean values theorem at all. So I guess we could just go ahead and show this as a corollary. There are, of course, other ways to prove the mean value theorem. It doesn't rely on Rolle's theorem, so it's not technically circular. But I mean, this is just an easy corollary of the mean value theorem. By the mean value theorem, f prime of c equals f of b minus f of a over b minus a. F of b is equal to f of a, so this is 0. All right. So there is a c from the mean value theorem that f prime of c is equal to 0. Okay. So this is a good one to test out. Like, you could just try drawing any continuous function where the endpoints are equal, they're at the same level, and you'll see somewhere it has to level out somewhere, right? It has to have a horizontal tangent at some point where the derivative would be 0. So, if we look like this, for example, we could look at this point and this point, right? So here f of a equals f of b, then the secant line between these points would be a horizontal line, which has slope 0. And right here is where it starts to level out, and we would also see a slope of 0. And we're going to look more at this too, where you have these, the maxes and mins, and how that relates to the slope being 0. But same idea on this side. If we look at these points, then again, this point is where it levels out, and you'd have a horizontal tangent, which would be parallel to that point, that secant line, meaning this secant line. And you would have f prime of c being 0 at that point.